All right, let's take a look at a basic Rysberg formula example problem. This is one of those ones where if you use the formula I give you in the lecture as opposed to the one the book gives you, it'll save you a lot of time. They're wanting to know for an electron transitioning from n equals 3 to n equals 8 in the hydrogen atom, calculate the change in energy. Well, the formula I gave you in lecture is that the change in energy is equal to the opposite of the Rysberg constant times 1 over n squared final minus 1 over n squared initial. When you use the energy version of this formula, the one I gave you in lecture, you have to use a Rysberg constant given to you in energy. If you use the Rysberg constant your book gives you, that's in inverse nanometers, which is a pain in the butt and requires you to go through a bunch more extra steps. One of the many awesome times listening to my lectures helps you out and saves you a little bit of time. Because in lecture, I give you that Rysberg constant in terms of joules. So you can just plug it into the formula directly. So let's plug and chug now that we've got our formula. We've got our change in energy equals 2.178 times 10 to, and also let me say, if you asked about this question, good job, because I get asked about this question every semester, right? So the fact that you asked about it actually shows that you're right with everybody else. You're working along where you need to be, and you've gotten here and you have questions about it. That's perfectly normal, perfectly typical. I expect it every semester. So if you've asked about this, good job. Now, I don't mean that sarcastically. I'm very serious. It shows that you are right where you need to be. You're understanding the material, and we're going to straighten this out for you, and you'll understand this a lot better after this tutorial here. All right, so we've got our constant. We're going to plug it in for Rysberg. Our final state here, and this is where it's a little bit different from what we've seen in lecture. Here the electron's going from n equals 3 to n equals 8. So our electron is moving up. And to move up, it has to absorb energy. So we're going to see an endothermic process going on here, which means our final answer, if we've done it correctly, should have a positive change in energy. It starts off, well, sorry, it goes from 3 to 8. So its final state is the 8. So 1 over 8 squared minus 1 over the initial state squared. So that's 3 squared. So we have delta E equals to negative 2.178 times 10 to the negative 18th joules over 1 over 64 minus 1 over 9. Now I'm going to simplify the term in parentheses. So I get that. Now I'm going to multiply by my constant. And that's going to give me a need for a new screen. That's going to give me delta E equals a oops, sorry. Yeah, that's a negative, by the way. And a negative times a negative is positive, because -9 is larger than -6. Whatever. I'm sorry. And that should be a negative 0.095, whatever. Times a negative 2.17, not 2. This is what you should show out of your calculator: 2.0796875 times 10 to the negative 19th joules. Let me address two things. What happened to our negative signs? Well, 1/64 minus 1/9 gives you that negative 0.095. So that term's negative, and then we have the negative sign built into our formula. And a negative times a negative equals a positive. Mathematical proof that two rights do in fact make a wrong. I mean, two wrongs do in fact make a right. So our final answer, when we multiply these two terms, winds up being positive. Now we go to the sticky wicket of sig figs. Well, these 3 and 5s up here are integers, and they're exact. So they don't actually factor into our sig figs. So really, the only thing that affects our number of sig figs is the number of place values in the Reisenberg constant, or the version of the Reisenberg constant that we looked up. This one has 4, so we're going to have 4 sig figs. 1, 2, 3, 4. You're rounding that 9 on the basis of a 6, so 2.080 times 10 to the negative 19 joules. That's it. Beep.